Hello, everyone. Welcome back to Physics 60-second meeting, second session. We had the first session, and in between, we have an off the cuff with Antonio Lau, and which is so amazing because she was telling us about what ought to be done and the earth changes and all. Wow, it's so amazing. So here we are. We're doing a three session today in a 60-second physics meeting. And this is the third session. So without much ado, I'll quickly share screen with my PowerPoint presentation so you can see the agenda of the second session. Okay, and then we will start it off immediately. And the agenda for our second session, we've completed the first one with Antonia, as well as Dave Rexel, the CEO of Habitus Building System. And now there's a second session, or rather the third session, because there's a second session in between that Antonia just done. So the second session here, we have the Physics Steering Committee planning the first physics energy device, a free energy device training program with Patrick Kelly introducing the concept of the device, followed by a presentation by Pontus, I would say, on his preparation in building the first prototype of Thomas Buie's Buie-Morin motor generator. Unfortunately, Thomas is not available for this session, so we will do the honors of doing the meeting without him this time. Okay, and then having done that, okay, then we will adjourn to the next meeting, which is the 63rd physics meeting on the 2nd of April. And you realize the 2nd April is a Tuesday because Pontus is celebrating his dad's birthday, who was 90 years old, on the 3rd of April. So we are agreeing to have this meeting on Tuesday. So please take note, okay? Right, so that's it. And I'm going to stop sharing. Hey, I'm back here on the Zoom room with you all. I'm sorry, this is me, Crystal. Hi. All right. So, right. So I have done the agenda of this second session. Now, I would like to call upon Patrick Kelly to do the introduction or walk us through with the documentation that he's come up with. Patrick is amazing. He actually took a lot of time and trouble to look through all of Thomas Buie's videos in Thomas Buie's YouTube channel to understand very well and very deeply of how the system works, this Buie-Morin motor generator works, and the concept itself. So if you don't know Patrick Kelly, please go to our website and click on the links. He is amazing with his ebook. He's written 3,000 to 4,000 pages of all the free energy, alternative energy devices that had been compiled by him from all over the world. And we use his ebook like a textbook, all of us who are into free energy and alternative energy. So there you go. So Patrick has done this documentation in his website called Chapter 32. So if you go to his website, which you can find in physics page link, you will be able to find Chapter 32. Patrick's website is, I will get him to tell you while I share screen later. So now, without much to say anymore, can I pass the microphone over to Patrick? Patrick, please.
Thank you very much.
You're welcome.
I need to share a screen on this particular operation. Can you hear me all right verbally?
Yes, we can hear you clearly. Thank you.
That's a pleasant change. Okay. You should be able to see this PDF display, okay? Is that right?
No.
Not yet.
You can't see a PDF display?
No.
Okay.
Got to click on share.
I did click on share. I have to try and click on share again, but it doesn't want to show me.
If you can't do it, I can do the job.
Okay. Let's see if we go again. Can you see it now?
Yes.
You can see the PDF on screen.
Yes, we can see it now.
Okay, that's a pleasant change. Okay, this is just a simple introductory description of Thomas's design. Thomas Buie of America and Gerard Morin of Canada both worked on developing a self-powered system which provides kilowatts of excess power to power other equipment. Thomas feels strongly that water and electricity are part of a person's rights and not a privilege which has to be paid for. They developed this self-powered generator in order to supply the electric needs of a household. First, we need to know what sort of power is used by typical household appliances, and perhaps the following illustration would help. And let me apologize if you're already expert in electrical things, but surprisingly, I find an awful lot of people have not the slightest idea what sort of power levels are being used. In a household, if you want to charge your mobile phone, you might use 10 watts. If you're running a radio off electricity, it might be 30 watts, depending on how high the sound level is set. If you're running a fan in countries that need cooling, which do not include where I live, you might be running, say, 50 watts for a fan, up to 100 watts typically for a large fan. If you're lighting light bulbs, then typically a good light bulb might be 100 watts. If you're running a television set, a large television set, it could be 150 watts. If you're running a refrigerator, it could be 600 watts, but a refrigerator is off most of the time, unless you're in a very, very hot country. When you're boiling,
can I say something about the refrigerator? I'm just buying a new one now, and the new Samsung, the big one with 2 doors, and the ice crush machine in the door is between 44 watts to 50 watts. You checked it up, it is not 600 anymore if you buy a new one.
Okay.
Here I go for free almost.
Thank you. If you're running a kettle for cups of tea, it can be typically 1500 watts to run the kettle when it's boiling water. If you're using, say, a deep fat fryer, it could be 1800 watts typically. If you're using a fire, an electric fire, it's usually 1000 watts for a single bar, 2000 watts for 2 bars. If you're running a washing machine, it's typically just over 2000 watts, typically 2200 or so. If you're running a tumble dryer, a large one, it's of the same sort of order, about 2500 watts. If you're running a cooker, it's difficult to say. It depends on what you have switched on. But typically, you would expect to be supplying at least 3000 watts and maybe up to 6000 watts, depending on the cooker and what you're doing. If you're running a shower, which heats the water as it pumps it out, it would be typically about 3000 watts, as would be an air conditioning unit. Those power levels are only approximate, as many devices have different power settings which the user can select. For example, in Iraq during the night, some households have communal air conditioning for only 1000 watts. Americans have daytime air conditioning, usually of at least 3000 watts, while in Britain, almost no households have any kind of air conditioning, while some adults in India don't even know what an electric fire is. Anyway, it would be nice to be able to power electrical equipment without having to pay for electricity. And that's what this system allows you to do. Whether it is the 120 volts, 60 cycles per second used in America, or the 240 volt, 50 cycles per second used in the rest of the world. The self-powered electricity generator, which can provide you with free electricity, is essentially very simple in outline. A battery is used to power a standard DC to AC inverter. Then the voltage is stepped up to around 400 volts. Next, a special controller is used to feed that 400 volts to a powerful motor at high frequency. And finally, the motor is used to spin an AC generator, which is called an alternator, which produces the electricity which we want. Part of that electricity is fed back to the battery and the inverter. The battery gets very little of it because it's only on very briefly. The inverter takes most of the current, and that sustains the system. The magic in this system is caused by the high voltage and the high-speed pulses with which that voltage is applied to a carefully chosen type of motor. With 700 watts of input power, the system puts out 10,000 watts of output power. The most important components of this system are the controller and the motor. You're probably familiar with the most common type of motor, which is a single-phase motor. But the more powerful motors used in industry are three-phase motors. There are several varieties of three-phase motors, but the one which we want to use has 36 coils connected in 3 sets of 12 windings connected in parallel, that is, across each other. This is a very powerful arrangement, as sending one pulse of current to each of these 3 chains only advances the motor by 30 degrees. In other words, you have to give 12 pulses to get one full rotation. There's a continuous ring of magnets immediately outside the coils and the periphery of the casing. This motor is used in a Samsung washing machine. A 3-phase motor sounds very technical, but really it isn't. It's just a motor which has got 3 sets of drive coils instead of just one coil. The first set of coils are shown marked in red here. Every 3rd coil is in that set. The coil set 1 has 12 coils, all wired in parallel so that they act as a single coil. Coil set 2 is marked in blue. They're the coils next to the coil set 1. They also are 12 coils, all wired in one parallel set, so that they act as a single coil. Coil set 3, marked in yellow here, again is 12 coils, all wired in parallel so that they act as a single coil. So the motor has effectively just 3 coils, and it is made to go round by pulsing the coils in order. That is, coil number 1, then coil set number 2, then coil set number 3, then coil set 1 again, and so on. The more rapidly the coils are pulsed, the faster the motor rotates. And in this system, that rotation can be very fast indeed. The pulsing of those 3 coil sets, one after the other in sequence, is done by the controller unit, which is a key component in this design. The motor is a permanent magnet, synchronous motor, which has no sensors built into it. That sounds ever so impressive, but it's actually the cheapest type of 3-phase motor, and because it has no sensors, it is the most difficult motor to drive reliably. There are several varieties of 3-phase motors, but the one we want to use has 36 coils connected as 3 sets of 12 coils in parallel. The controller consists of 2 parts. The first is an Arduino board, which is a general-purpose development board, and is essentially a simple computer which can be programmed from an ordinary computer or a laptop. It holds the program in its memory, and it runs it continuously when it's started. The second part is an electronics link between the Arduino board and the motor. That link boosts the power fed to the motor using high-powered transistors which can feed high currents to the motor. And there are some other wires which feed information back to the Arduino board to give it full control of what's happening with the motor. The Arduino program powers the motor coils in sequence, and as well as that, it senses the position of the actual rotor as it spins. It does that by sensing the voltages in each of the 3 coil sets at all times. The Samsung motor is available as a spare part if you want to buy it new. It's not necessary for you to become an expert programmer of any Arduino board, as the program used is provided for you. A good instruction video on how to feed a program into the Arduino Uno board is shown on YouTube at this particular link. There are 184 lines of Arduino code, just a little bit of which is shown underneath. It comes from the simplecircuit.com web page. It starts off with some comments saying this is a free software without any warranty. Then it launches into defining its own terms, speed up and speed down and so on. And it goes on for 184 lines. But you don't need to know that. You can just take the program and feed it directly into the Arduino, which is a computer. And the one that's used in this design is the Arduino Uno, release number 3. The board itself looks like this. It's the Uno board. It has the computer in a single large chip plugged into the board. It has various components, including a crystal which controls the frequency, and it can be interfaced to the motor itself. One way of doing it is using a computer chip called an IR2104. We need to connect up this Arduino Uno to drive one of the 3 phases of our 3-phase motor. So to do that, we would use an IR2104 driver chip and an IRF840 field effect transistor, that's a FET, to feed our 400-volt power supply to the motor. The power drive for the first phase is like this. This is what the IRF840 looks like. It has 3 pins coming out of it. The first one is a grid, the second one is a drain, and the third one is a source. And that's what your IR2104 chip looks like, and that's the way that it's connected inside. Just pay attention to the actual numbers applied to the pins on the chip. They're in sequence going anti-clockwise when you look down on it from the top. The top has got an indentation in the surface, which you can see there. That shows you which end chip pin number 1 starts at. So you've got 1, 2, 3, 4 on this side. Then round the far side, you've got 5, 6, 7, and 8. And those are the actual connections inside. Not that you need to really concern yourself with that. What effectively we do is we connect the IR2104 chip to 2 particular connectors on the Arduino board. We have 2 capacitors and 1 little diode, which is a 1N4148. And then the output from the IR2104 goes through a 100 ohm resistor to 1 transistor to handle the positive part of the signal, and this is the equivalent 100 ohm and another transistor to handle the negative going part. And that feeds out directly to your motor, connecting as phase 1. Now that's how the thing actually works. The 1N4148 diode is very cheap and it's very fast operating. It operates in just 4 nanoseconds. Because of its very high performance, so many are made that it's also very cheap, typically about 3 pence each. The drive for this second section, this phase 2 of the motor, is almost identical. It's just different connections to the points on the board, and then exactly the same circuit is used and fed this time to phase 2 of the motor. Surprise, surprise. The drive for the third phase is identical, except that it's connected to two different connection points on the Arduino Uno board. Circuit is exactly the same, very simple. The 100 ohm resistors feed into the grids of the two transistors, and the combined output is fed across to the phase 3 connection of the motor. We also need to provide the Arduino board with feedback information to let it know where the motor is in its rotation. And that's done by sensing the phase connections to the motor like this. You have phase 1, but the voltage is divided down 33 to 10. So only a quarter of the voltage fed to phase 1 is fed back to the Arduino board. Also, with the large resistor in the path, it's fed back to a second point of the Arduino board. The same voltage divider, 33 to 10, is used to drop the voltage level on phase 3, and the same on phase 2. And all those three are combined and fed into the connector 6 on the board. You needn't worry unduly about these things. These are taken care of in the program. The connections run across to the Arduino board, and you have a ground connection, which is the negative side of the battery. And it goes to the connector here on the board, which is cunningly marked GND for ground. You then have two push-button switches, one for making the board go faster, one for making the board go slower, and they both connect to the same point. All these points here with the little triangular devices on it are actually going to the ground connection. They're all the same point. We have a bit of warning here. You can get a shock from any voltage above 30 volts. If the voltage is alternating current at a frequency under 100 cycles per second, that's the sort that's supplied by your mains wall socket, then that shock can be very serious. The power supply described here is very easy to understand and to make, but if you get a shock from it, that shock is very likely to kill you. So here's a disclaimer. You personally are responsible for your own actions. This presentation is for information purposes only. And if you decide to make or experiment with voltages higher than 12 volts, then you and you alone are responsible for your actions. And neither the author, the web hosting service, nor anyone else is responsible for what you do or for any damage or injury caused by your own actions. Having said that, please understand that if you're careful and sensible, there's no danger in constructing this power generator in spite of the very high 400 volt input to this power driver circuit. To stay safe, you make all the necessary connections and insulate them before you apply power. So we need to construct an electronics component board to connect the Arduino to the phases of the motor. Please remember that this board will be carrying 400 volts, and so you need to enclose the board in a plastic box before powering it up. Thomas Buie describes the power supply method which he has used successfully in the past. It's a very simple arrangement which uses readily available parts which can be purchased easily through the internet. This is the diagram here for those particular components. The first component is a car battery. Car battery can supply a very large amount of current, but only for a short time. It's typically 12 volts. That feeds across to an inverter. These are very common on the market because they're used a lot connected to car batteries to provide power for things like USB sockets, radios, computers, and so on. If you have a European inverter, it will raise the 12 volts to about 220 volts. If you apply that to the input of a 2-to-1 transformer, that will raise the voltage to about 440 volts AC. You then pass it through a rectifier system, which will produce about 440 volts DC when under load. You also take some of the inverter power, about 70 amps of it typically, and pass it through a heavy-duty battery charger and pass it back to the junction between the battery and the inverter. That's to here. Now, that looks as if you're going to supply an enormous current to the battery, but that isn't actually the case. The battery will get a little bit of it, but the bulk of the 70 amps coming back goes straight into the inverter and back around the system again, back in a circle. And that's what makes this system self-sustaining and self-powered. So the best thing to do is to get a European style inverter. The one that's shown in this particular picture here, it can supply up to 2,000 watts continuously and 4,000 watts for a peak output. It's also cheap at £25 delivered to your home, and it has two handy USB outputs. However, we want 400 volts or more at 1 amp or slightly more. Now that's about 800 watts for a 12-volt inverter like this. Thomas has used a transformer to raise the voltage higher. It is possible to get them. They're used as 2-to-1 step-down or step-up transformers, and it's easy enough to get one of sufficient power range. The 400 volts AC is fed into 4 diodes, which is called a bridge, and the output is smoothed by a capacitor of high voltage. It doesn't matter how the 400 volts is generated. We need to feed some 70 amps back to the battery and the inverter output to sustain the motor indefinitely. This capacitor here, which we want to be high voltage, is not that easy to get, so we would probably use 2 capacitors in series, 2 400 volt capacitors, which are easy to get and are not particularly expensive. But the level of feedback current is much higher than any ordinary battery charger can supply. Typical battery charger will do less than 10 amps. So we're talking about a professional level charger able to deliver some 700 watts of continuous power. So you're talking about a unit big enough to need wheels and a pulling handle to move it around. We come now to the alternator, which produces the electrical output, which is the whole point of the system. All of the components and methods described so far have the objective of spinning the alternator indefinitely in order to provide electrical power for a household. However, please understand clearly that your local power company is most unlikely to allow you to connect your generator up to their wiring, which goes to your fuse box. Consequently, it's better if you use your new supply of electrical power as if it were an emergency backup generator. That is, you connect it up to your appliances without connecting it to any external power supply or wall socket. The system described so far is perfectly capable of driving an alternator of any power level up to 10 kilowatts without altering any of the components. So the size of the alternator which you buy is up to you. Personally, I would consider an output of 5 kilowatts as being adequate to excessive, but then my electrical needs are probably lower than yours might be. Anyway, in the UK, one supplier is Machine Mart, and they offer 3 different alternators. They look like this, and each needs to be driven at 3,000 revs per second. This one here, which is 6.6 kVA, which is kilovolt amps. it costs £324, and the pulley to go on the shaft, if you use one, would be £15. The smaller versions, 3.5 kilovolt amps, is £288, which is not a lot cheaper. The smallest they have is 2.2 kilovolt amps, and it's £240. And the pulley belts and so on are about £15. Looking at the small price difference between the alternators, there seems to be very little reason not to pick the 6.5 kVA units, even if your expected current is likely to be well below that rating. The unit kVA is the same as kilowatts if, and only if, the equipment which is being powered has a power factor of 1. That sounds very technical, but all that means is that the equipment being powered has no coils in it. So we're really talking about light bulbs. Equipment like vacuum cleaners, washing machines, tumble dryers, fans, etc. do not have a power factor of 1. And so a 6.5 kVA alternator is generally considered to have about 5 kilowatts of output power. The final step is to mount the motor, unit and alternator together so that the motor can drive the alternator to provide the electrical output current. If you're a very slick mechanical operator, you can align the alternator shaft with the motor and it can drive it directly. But that is very, very difficult to do because the very slightest difference between the alignment of the shafts causes major vibration and wear. The easy way is to use a pulley and a belt like used in your car. We need to thank Thomas Buie for sharing his design freely. However, there is one issue which needs to be dealt with, and that is the plastic construction of parts of the motor. The motor was intended to power a washing machine, and because that operation is slow and the mechanical stresses involved are fairly low, plastic was used connecting it to the washing machine. In this application, the stresses are much higher, and the usage is all day, every day, as opposed to the occasional use of a washing machine. So it's necessary to provide a mild steel or aluminium shaft in order to drive the larger sizes of alternator. Machining by a local steel fabrication shop may be necessary unless you already own a lathe or have access to one. This is the drive piece made in plastic that comes with the washing machine. We need to put a metal piece on top of that and bolt it to the motor, giving a drive shaft and a bearing at the far side. This is what the unit looks like when you've done that, and this results in a very robust and powerful motor which is ready to drive a large alternator. Let me stress that if you construct a generator system like this, you do not connect it to the wiring of the local electricity power supply company. For example, the electrical main supply wiring will come into your household fuse box or contact breaker box. Do not connect your generator wiring to that same box, but instead treat your generator in the same way as an emergency generator, feeding the output directly to your washing machine, electric heater, or whatever, through an extension cable and not through a wall socket. This is just a quick outline of how the system works. Thomas will fill in additional details, and in the interactive video conferencing training sessions being prepared by the Free Energy Special Interest Group, questions will be answered and more powerful circuitry will be shown and explained. And that is a simple introduction as to how the system works.
Oh, thank you very much, Patrick. Oh, isn't this so concise and it's so well prepared. Thank you, Patrick, that everyone now has a very good understanding of how the Buie-Morin motor generator is going to work. So I think because there's less than like 1 minute, less than 2 minutes, 1 minute left, we will have to adjourn this meeting to the next meeting. So Pontus can then get Thomas Buie to come in to explain the details and to show his lab live, the equipment and the materials and the whatever that is needed to put together this unit to work and function in the next meeting. That will be Physics 63rd meeting on the 2nd of April. Okay, it's the 2nd of April, not the 3rd. It's a Tuesday for the next meeting. It's a one-off in April, okay? And I would like to say, so we have less than 1 minute left, and I would like to thank you again, Patrick, for doing such a wonderful documentation of a presentation here that you walk us through with. And I would like to thank everyone as well here for attending this meeting. So this meeting, there being no other business, this 62nd FESIG meeting is now adjourned to the 63rd FESIG meeting on the 2nd of April. And thank you, James, for hosting the Zoom room. Namaste in Lakesh. Namaskar, everyone. Thank you. Patrick, will you stop sharing?
I would if I could. How do you do it?
Couldn't. All right. It's okay. I just want to say that we are also